I'm me still. And yeah, so I've been here for about 10 years in Austin. And I do work for Department of Defense at a small company called Umbra. And I also do independent consulting work. And we're here today to talk about how we can make large language models more cool. Why would it say bunk, bunk? Huh. Doesn't like the cursor. It will not extend. Why? Okay, because I got to say got it. Okay. All right. No. That is weird. Maybe it'll let me do that. Oh, that's going to be really annoying. Okay, well, so it is. All right, so our talk is in 3 parts. So how do LLMs think? We'll go a little bit in detail. And then we'll talk about how we can ground LLMs in a cognitive foundation, because these things are just trained on the internet, right? Whereas human children learn by knocking stuff around and throwing things. And then we'll talk about how we can expand LLMs with GOFAI. And a little bit of that is like Sophia talked about, how they can use tools. But then we'll also talk about what comes after using tools. And so there's really 3 technologies, in my view, that enabled ChatGPT. So the first one was language modeling. The second was transformers, and the third being instruction tuning. So we'll go through each of those. And yes. So it all began with machine translation. So you have something like the patient fell, and what was it, 2012 or so, recurrent neural networks started becoming popular. And so you take the word the, which has some embedding, some vector, like 512 dimension vector, and you say, okay, let me get the vector for the. And then given the vector for the, and the vector for patient, you have a neural network here that combines them into some new vector that represents the sentence so far, the patient. And you keep going, the patient fell, and then you end up at H3 with a vector that represents this sentence. And that's an encoder RNN. And then you take a decoder RNN, and you start with H3, that vector that we encoded before, and now you can translate it into Spanish. And the reason we can do this is because there's a lot of text on the internet, English to Spanish. And so the thing can just learn without having to bother humans. And so, you know, it says, okay, given this vector, what's the most likely word? And it's going to say, okay, well, the neural network is going to say L. And then given this vector and the vector for L, it computes a new vector for it in the decoding. And then it says, okay, given that new vector, that representation, paciente is the next one. And then it just keeps going until it hits an end token, right? So, this allowed machine translation to finally work. So before this point, we used to all make fun of machine translation. It was hilarious. And then it actually started to kind of work. It's still not as good as a professional human, but it's now serviceable. So one thing that started making this process work better, they found, was that if you're at this point when you're producing say, if you can not only look at the previous vector, but all of the encoded vectors, they called that attention. And suddenly, by paying attention to more information, it could do better, right? And so then translation started working even better. And then they're like, well, why bother with the RNN at all? Attention is all you need, right? So you guys probably remember this paper. And so transformers is that second big technology. And we're going to look into that in a little bit of detail. So, so you have the same thing going on here. You have the patient and maybe a question mark here. You want to fill this in, and she, right? So in a transformer architecture, what you do is you get this key query value vector for, oh my goodness, let's see. The room is available all day, but okay, so you get this key query value vector, and we'll go over in a minute how that comes about. And then you can start looking, just like we saw in the attention previews, you can start looking what's nearby, right? And then, and what you do is you take the key, you take the query for this vector, and you grab the key. I mean, you compare it with the key, and you get a weight. And then that weight gets multiplied by the value, and all those get summed to get this at the next level. So let's look a little deeper at that. So what you have is, so we recall from college that when you do matrix multiplication, you have m times n, and then times n times o, and then you get another matrix of m times o, right? And this is how I like to think about this kind of stuff, because I really like that little pattern. And so if we consider like a vocab size of 1,000, I'm sorry, a vocab size of like 50,000, and a embedding size of like 1,000, and a length of input tokens, maybe a window of like 100, right? Then what we have is, if we ignore all the multiple heads and the multiple layers, we have an embedding matrix of size, vocab size by the dimension. We have a query matrix of size, dimension by the dimension of the key, a key matrix of size, dimension by dimension of key, and a value matrix of dimension of the value. And then we have this kind of linear matrix on the end. So what transformers, when they're learning these matrices, and these matrices are initially randomized with just random stuff. And there's a bunch of different tricks you can use. Used to talk about that like 10 years ago. You don't hear about it so much anymore. But and then what you do is, the first thing you do is you get the words, and you get an embedding matrix of size L by D, which is the length of the input tokens, right? So you get an embedding matrix. Then you take that matrix and you compute the keys, queries, and values by doing a matrix multiplication. So if you look over here, you've got this Q coming from X, and then D, and then you use that nice little pattern that I like, L times D, D times K, and then you end up with L times D, K. That's the size, of course. And you do the same for the keys. Okay, so now you have these three matrices with these three learned parameters taken from your input data. And now you do the actual attention. So you can compute this Q times K transpose, and you end up with something L by L. And these are actually the scalar weights that we saw back up here. And then, so then you can use the weights times the values. The weights times the values, and then you can rescale it so that you're ready for the next layer. And then there's like skip layers and linear stuff. And what is the linear stuff? But that is like the basic of what's going on. And I really like looking at it this way, because what you're really trying to do is you're doing a search through this space of parameters to find the ones that match the training data best. And of course, the training data is just the internet, right? And then of course it uses gradient descent and calculus, right? The chain rule. And that's what's going on there. So that works really great. And so what we see now, this should make a little more sense, is you've got the patient. And so what you've got is you got the results of that vector, the key, query, and value. All those things are like rows in those vectors that we saw on the previous slide. And then you can take, and this is a nominal way of looking at it, but what's really happening under the hood is vector multiplication, right? I'm sorry, matrix multiplication. And so, and then you get the weighted value. So you get the key times the query is a weight. So how much does this guy match with this person here? And then how much, and then that weight says, okay, if they match a lot, then use the value that comes out of that a lot. So it's like addressing some area of memory and say, oh, this memory area is relevant to this. Okay. So that is the second technology. Now, the third technology that really made ChatGPT pop, or really made it amazing, is this instruction tuning. So what you have without instruction tuning is a language model, And all that a language model can do is it can continue on what you put into it at the beginning, or it could fill in what's missing. But it doesn't have that sense of, oh, I'm a helpful chatbot and I'll help you do stuff and all that. That all comes from the instruction tuning. And if you try models that have not been instruction tuned, you notice a big difference in how useful they are in terms of it, if you're using them for like just general chat stuff, right? And that chat, one of the main things that OpenAI did is they really did a great job of this instruction tuning. And there are other open LLMs. What was it? The Open Assistant is trying to catch up. But this is where they have their biggest lead so far. And so the way that works is you train an evaluation model to determine how good an output is. So if you train just directly on generating good outputs, you're limited because the agent can't explore, so to speak. So what you really want to do is create a model that can tell you whether or not what the agent generated is good. And that's where the human comes into play. Reinforcement learning with human feedback. So you have humans rate outputs, and then from these ratings of the outputs on the language model, you create a new model that basically can take an output from a language model and say, hey, that's a good response or not a great response. When you have that second model, then what the heck? All right. When you have that second model, then you can just let the algorithm do autonomous learning. So it's training itself. It's got some model that says whether or not it's doing a good job. You train the parent, a robot parent, and then this robot parent can, no matter what this thing generates, determine whether or not it did a good job. And this is where a lot of the power comes from. And this is what really helped take a language model and make it useful. Okay, so those are the main thing. Now I'll take a little bit into reinforcement learning, because reinforcement learning is used for this. Most people are familiar, but yes.
I'm curious, how much do we know about the ChatGPT second model, the evaluation model? Like, how big is it? Is it all in complexity levels of ChatGPT itself, or is it much, much smaller?
I think it's smaller. I don't think we know details. All I know is from the blog post. Give away all my stuff here. From this, I'm going to put these slides online and I'll tweet it. So there's a blog post here, and then a paper, and that's about all we know. They're big, but I don't think the size of the model is the limiting factor. I think the size of the model is the limiting factor is the data to train. So they hired a bunch of people, I think, overseas to do a lot of stuff, and that's what Open Assistant has tried to mimic by using the community. And then with that data set, I think you can get pretty close.
What's the scale of humans involved in that? Like when you say hired a bunch of people, 100, 1,000, 10,000?
Yeah, they don't say. But Open Assistant does say. So Open Assistant, and I don't know, but I think they have I would want to say 100,000 different examples. That could be wrong, but we could just Google. It's Open Assistant, the Yannick guy. It's a lot. Yeah, it's very frustrating that OpenAI doesn't tell us what they're doing. Yeah. All right. So, but the second model that's training the first one is using reinforcement learning, and reinforcement learning is a gradual stamping in of behavior. So it was first started looking at with animals in 1898, and then in the 20th century there was behaviorism was all the rage. With Skinner, and they had all these rats in the boxes, and they wanted to say, all you care about is how many times you can shock the rat and have it learn which thing. And then it got formulated into artificial intelligence in 1998. Well, I mean, before that there were papers, but the seminal book in 1998 by Sutton and Bartow. And the way that works is, at its most trivial, is you've got like a thing taking actions in the world in some state. And then, wow, this thing doesn't work very well. Okay, it takes actions in the world and it just kind of randomly wanders around. And when it gets to the gold, it gets a reward. So it doesn't get a reward at every time step like supervised learning does. it only gets a reward occasionally. And so you can imagine this is similar to generating text. You only get a reward at the end if it determines whether or not it's a good text or not, right? You don't get a reward at every word you generate. So, and what that does is you feed that back. And you say, okay, well, I got a reward here, so this state is pretty good. And this state's a little less good, and this state's a little less good, and all the way back, right? And do that untold number of times. And then you end up with a policy for the whole space. And that policy now is represented as a neural network. But that's what's going on in this second step too, this reinforcement learning. Okay, so that is, quote, how they think, if you're really loose with the term think. And I've never had a good definition of think, so that's fine with me. Okay, so then the second thing is, okay, how can we train these things better, right? They're trained just on the internet. Can we do better? And so maybe we can do like a curriculum learning on the real world. So instead of having tokens down here, we actually have the world as it's looking at, because this is how evolution trained us. So instead of having words, we've got the little images. And so we, of course, evolved, we first had like the first purpose came about when somehow some sensor hooked to some effector, right? Just by random chance, and the cell could take a gradient towards food, right? So we started to have some purpose. And so if we were going to do curriculum learning to try to give LLMs like a deeper understanding of their environment, we might want to start with saying, okay, some things you want to predict are more important than others. Like for us, we want to predict what's going to lead, or our amoeba ancestors wanted to predict what's going to lead us to more resources and away from threats, right? That was the most important thing, so we can maintain metabolism. Of course, then if we go up a little bit, we have development of mind. And so there's a famous result by Spelke, Elizabeth Spelke, and she determined there was an ontology used by the human mind. And the way they did this is they took babies right from birth, right from their parents. I don't know who would give their baby up right after birth, but, and they said, they showed baby stuff and they figured out what surprised a baby. So if something surprised a baby, that meant it was innate. And the way they know, you can't just ask a baby if it's surprising, but the way they know something surprises a baby, like if something goes under the table and it comes back up as a different object, that would surprise a baby, right? These glasses go under here and they come up as a teddy bear, that's going to surprise the baby. And they know that because babies look longer at surprising things, right? So using that very simple thing, they were able to say, okay, babies know places, objects, forms, agents, social patterns, and numbers, right? So that's one thing. If we're going to talk about developing a language model that actually understands the world in a deeper sense, that's one thing we want to consider. And there's also another body of work on image schemas and stuff, which is like perceptual patterns that are kind of grounded, that kind of ground how we understand the world, like force and inside and out. So if someone says, oh, he forced me, or the broken air conditioner forced me to move my meeting. So these people argue that, and I believe it, that deep inside, we have force understood as some physical force, and we, through a metaphor, understand what that means. So what we want to do is we want to encourage language models to get that kind of deep understanding. And so, wow, this thing is, okay. So one way we can do that is curriculum learning and having data that represents like basic objects and relationships and interactions. Okay, and then the next on top of that is like the pre-literate learning. All of the things we learn after we're born, after Spelke takes us as a baby, and she puts us back in our house, and then we run around the house and knock things over. We learn all this other stuff. And so this is the properties of specific kinds of objects. So if you're training an LLM for manufacturing, this is where you would start introducing things specific to manufacturing, right? And say, there's objects that can be in certain spots and it takes longer to reach them and that kind of thing. And so, in fact, there's a paper that just came out a couple of days ago called Tiny Models. And what they found is that if they train a language model just on very simple stories that a 3 or 4-year-old can understand, they can get a much smaller model to generate coherent text than is possible if you train it on general text, right? And which makes sense, because when we're 3 or 4, our brains are actually smaller, right? Many parts haven't come online yet. So it's a really cool result and in the right direction, in my opinion. Okay, and then of course, that's not how we don't do any of this at all the way we train LLMs now. We just send them on the internet, which the internet floats on top of all this stuff. And so when you write on the internet, you assume the reader has this cognitive foundation, and you leave out a lot of stuff. And so I'm amazed that LLMs can do as well as they can, given that they don't have this stuff. And so if we give them this stuff, I think they're going to be able to do a lot better. Okay, and there's people starting this process. So there's imitation learning from videos. So and the trick with that is the tokenization, right? So words, we have tokens, but at Google, they came up with a cool way to do tokens from video. So they can take the video, and there's a mechanism that learns to tokenize the video in such a way that it makes sense to the robot, so it can predict what's going to happen next. And then the way that works is they take these images and they learn it, film through this token learner. And then once you have tokens, then of course you can just apply the standard stuff we've been doing with transformers. And then you can put it in a robot, which is on the way, right? Very cool. And then I'm most excited about the idea of training reinforcement learning in simulation, because if you're watching videos, you can't actually take actions in the world. You can't run little mini experiments like children do all the time when they throw the cup down and see if mom will get all excited, and she usually does, right? So you can run experiments in simulation. And then there's AI2 Thor by Alan AI, which is trying to mimic what a house would look like for a child. And simulations are getting better all the time. Like Flight Simulator, this is my son's 10-year-old computer flying into Austin. You can probably recognize it, kind of, from ABIA. So it's pretty exciting. And I don't have an image for it because I wasn't sure about the rights of the image, but DeepMind is doing some amazing stuff with soccer. If you guys have seen the robots, they look just like kindergartners. They're like totally incompetent, barely understand, they're falling over all the time, but it's getting there. It's very cool. Robots both trained in simulation and then transferred into physical robots, playing soccer and knocking each other over. It's really great. And then Hugging Face has some decision transformers, so you can use the transformers for reinforcement learning. And we had a blog post about that about a year ago, where we had chickens and robots. And so I'm going to post these slides if you're interested in the blog post. Okay, so that is 2 of the 3 pieces. And the final one is expanding LLMs with GOFAI. So GOFAI, as many of you remember, is good old-fashioned artificial intelligence, right? So symbols and Prolog and Lisp and all that great stuff. So LLMs are, what LLMs have done is they're really great at what we do subconsciously. So when we started AI in the 1950s, we thought, okay, let me just think about how I put blocks on a table, and that must be how a robot does it. Or let me think about how I understand language or how I do computer vision, and that must be how a robot does it. But in reality, we don't have access to the ability of how we know how to pick up this thing, right? I don't really know how I do it. I think I do, but underneath is like an iceberg, right, of things that enable me to pick up this thing. And which is why when robots, it just doesn't work. And so you needed some sub-symbolic mechanism onto which the consciousness can float. So you know how you're like walking down the street and then you finally debug a problem that you weren't even thinking about. You're like, oh, it's that. It's because your subconsciousness is still following all the problems you had throughout the day. And sometimes it just pops up the answer, and it's great when that happens, right? And so LLMs now finally give AI that ability. So how can we then use it for us? So one way I think about cognition is we get some communication and we form a mental scene of what somebody says. So if I say, you know, the table is on the table, you may form a mental scene of that. That may be you may have an Excel spreadsheet on a table or a physical table on a table, right? We form some mental scene. And then we say, okay, given that mental scene, what are all the possibilities, right? And it seems to me if you have these pieces, then you have most of what you need to kind of understand and live in our world. So LLMs are great at forming that mental scene. We can't really access it, but they seem to be really good at it. When you type it in, they kind of seem to know what you mean, right? Even if they don't actually do a great job of knowing when they don't know the answer. But LLMs are less good at taking novel steps into the future. So they seem to be largely an interpolation of what's on the internet, but we want them to develop, you know, cures for new diseases and how to get us into space far away and all that. So they're going to need something else. And so, and this is an example, right? So if the table is on the table, and then there's like a little table on the table, and then so the possibilities are, like if you pick up the top table, you have to first walk to the table to do that, right? This is the kind of thing that would throw off a logic thing. Like you type in your logic and then you're like, oh, we have to actually walk over there. So you put that in. And then if you push the bottom table, the top table will fall. Okay. And then you get that in there and then, okay, well, party guests will think this is weird looking. Well, that's well beyond logic, right? But this is the kind of thing ChatGPT can understand. And so what we want to do is expand our LLM abilities with these tools. Now, this is an image from 2001: A Space Odyssey. If you haven't seen it, you should definitely watch at least the first 20 minutes. It's amazing. After that, it's kind of weird. But first 20 minutes is amazing. Okay, so there's kind of three different things we can do here. We can expand to tools, right? Like Wolfram Alpha, web search, and travel sites. And we just saw a talk on how to do that from Sophia, a practical way. And LangChain provides it, kind of packages all that up for us. So it's really cool. And then what if then the next step might be, well, what if we could have them write tools in first order logic? So if, you know, in AI, they started off, they're like, okay, well, I'm going to model the world. So I'm going to say if it's a bird, for all X, bird X implies can fly X. Okay, that's pretty cool. Look at all the stuff I've modeled, all these birds, and they can fly. And that's great. But then someone else comes around and says, okay, but not all birds can fly. Maybe like turkeys, right, don't fly. And so like, okay, no problem. Don't worry. If it's a bird and it's a flying bird, it can fly. And, you know, we humans can be confused about which birds are in flying birds or whatever. But in fact, if you guys remember WKRP, they had this thing where they flew. It was like a promotion for Thanksgiving for their radio station. So they flew a helicopter over downtown Cincinnati. And this guy threw out a bunch of turkeys. And people horrified watched the turkeys fall to their death. And the whole radio station is just terrified about what they just did. And he walks back in to the station and says, as God is my witness, I thought turkeys could fly. So, but this is unending, right? So if it's a bird and it's a flying bird, okay, and it doesn't have a broken wing, then it can fly. And this is why GOFAI failed, is because there's an unending set of things. No matter how you write out the model, it doesn't cover the next problem, right? And they're like, okay, well, what if it's covered in maple syrup? Okay, if it's not covered in maple syrup, right? And so what if then we could have LLMs write out these things? You give it the situation. We've talked about how it's good at getting the situation. And then it says, okay, I need to think forward. Let me write out these logical rules. And I've just built my own tool because then I can plug those logical rules into a theorem prover or into a planner or into, you know, something like Protege, or this is ECG Workbench. This is an old fashioned AI kind of way of representing natural language processing. Then we can get exactness. So I think that's going to be pretty exciting. And then we saw the example with Sophia of if you can plug it into Python, right? You have the power of Python. And then I'm particularly interested in, can we plug LLMs to create simulations in Unity? Because it's one thing to learn in the world, but it's another thing to completely imagine a world. So you say the table's on the table. And so this thing says, okay, I've never quite experienced what that's going to be. Let me just generate a random scene of a table on a table. And then it says, okay, now what happens if I apply force to the bottom table and the physics engine can take over and show it that the thing will fall? And then the robot can say, okay, yeah, this is dangerous for a toddler, right? That's the kind of thing that even though it never seen that, it could make that inference. That's pretty exciting to me. And there's been some tentative work in that direction, but I'm sure we'll see more. And so now to give a recap, there's 3 technologies that enable ChatGPT, right? The language modeling, which came from machine translation, transformers, which was just taking machine translation, throwing out the RNN and just doing attention, and then finally instruction tuning to make the language model do what we want to do, not just continue the text. And then we can deepen LLMs by building this cognitive foundation of trying to mimic the way that we actually learned about the world, and that would be a multimodal kind of experience where you would then have to tokenize words. And they literally, when they do that, they take video and they convert tokens, and those tokens have the same dimension as the words in your vector, in your embedding. So if you have somebody talking and somebody saying, here, this is a ball, it takes this is a ball, it takes the vector from this is a ball plus the picture of the ball and makes a vector of the ball. And then that gets fed into a language model, because the language model doesn't care what these tokens are, it's just trying to predict. And then finally, we've got our ape here with the bone, and we can enable tool use like we saw in the last talk. And maybe we can even have it write GOFAI planning code to see the world further, and maybe use simulation to kind of understand what things could happen if the world were in different places, kind of counterfactual in the Perl world. And that is my talk. Thank you. Any questions?
You know the specifics of the tiny models paper you mentioned earlier, like what sort of data they were training? What the scope of that set?
I didn't read the paper in full, but I think they said they used ChatGPT to make the data.
Gotcha.
So it might be something like use only the 10,000 most common words. You can do something like that to generate the data. And then I want to say like 10 million for parameter size, as opposed to like 200 billion for like ChatGPT. Yes.
What about more incremental updating to the weights as it goes, right? Like ChatGPT is what, 2 years old or whatever, right? But if we want something to summarize the news, it needs to be streaming in constantly information to build up new stuff. How do you see that?
Yeah, and that's a huge thing, because what people want, companies want, is they like, I want the power of ChatGPT, but I want to apply it to my private data, right? And I want it to work in my particular domain. And so there has been work on, you can just train a couple extra layers on top. The simplest thing is to just add it in the prompt. So you can add the information in the prompt. So like we saw in the last talk with LangChain, one thing you can do is you can take your private data and then put it in a vector database. And then whenever someone asks a question, you say, what documents in my vector database are most relevant to that question? You pull them in, a summary of those, into the actual prompt and send that to ChatGPT. And that way you don't have to retrain ChatGPT. Then the next level is adding, Laura, I think the college is a couple layers on top, where you just train a couple extra layers on top of ChatGPT to generate what you want. And then you can do fine tuning the whole thing, which is more expensive. And then you can also then run instruction tuning if you really have enough. Databricks, I think recently, a couple of weeks ago, made it a full instruction tune model. But then you have the question of, well, how do I get a GPU big enough to do that? And these things don't fit on your computer anymore, unfortunately, the bigger ones. And so you got to go like in the SageMaker or something like that and get this huge big GPU thing. But yep, that's definitely a thing that people are gravitating towards in business right now. Anything else?
So like on the simulation from like World of Warcraft or a massive multiplayer online game, do you think there are like simulated AIs playing right now?
Well, there probably have been for a while. You wouldn't need ChatGPT for that. There's been a lot of work like in StarCraft. A lot of people make StarCraft bots.
Yeah.
And they've been usually kind of rule-based bots, and there's been some, and of course, StarCraft, Alpha Star was a great example of that, where DeepMind created a StarCraft bot that could beat the best StarCraft player. So everybody's been using bots since then. Yeah, I mean, what was that old cartoon? No one on the internet knows you're a dog, right? It's even more so now. It's like with the AI. Yeah. And there's a question over here.
You mentioned about the layers of, what you learned as a kid and then kind of building on top of that. Isn't all of that already included in the information that you would feed in from the internet?
Not really. So the internet assumes the reader knows that. So the internet may say something like, the child came in and bumped the dinner table and where the guests were, right? And we all know that, ooh, that's bad because there might be wine glasses on that. But they don't have to say it because we all know it. We've all lived it. Or the internet might say, oh, and then he pushed the bottom pallet and all the other pallets fell down. And we know why that happens because we've seen blocks fall down, and we don't have to explain it when we write a story about it because we assume our reader already knows all that. And so it's been amazing to me that the models have done better as well as they've done, inferring what must be going on. But who knows what their actual mental model is underneath. And there's some debate about whether there is a mental model. It seems to me that there is starting to be one, but it can't be right because it's never lived in the world, but it's righter than it has any right to be so far. But I think we can get even better if we actually give it that experience. Yes.
I was reading something where a large language model given a prompt of like, how do you balance these little things? You get 9 eggs, a book, a nail, and a glass. You give this to GPT-3 and it says something nonsense, like put the nail down and then balance all the eggs. Book on top. But giving the same question to GPT-4, it's like put the eggs in a square, put the book up, nail, so it seems to be learning some foundational stuff about physics and the world.
It does, and it must be. Now, some people argue that, well, GPT-4 is just more powerful and it's seen more stories where those kind of like things have been laid out. But it does seem that I would guess there is some, with the power, it's able to infer some underlying physical mechanism. But as we all know, when you have to infer something, you might be wrong. So
Well, presumably they're using a different reward function too, but they're not back trained or like back applying the reward functions, are they?
I don't know about GPT-4 using any different mechanism other than being able to predict the next word. But some people, I think they're trained on images too, but it's unclear. You never know if you're using the one trained on images as well, or just the one trained on text. But yeah, the multimodal, I think, is going to make it have to infer less. And if it has to infer less, then maybe the models can be smaller, and then maybe we can get them back on our